We've seen that in one dimension, hitting times for Brownian motion of any height can be explicitly calculated in distribution and answer all sorts of very delicate questions about them. What about in higher dimensions? What can we say about Brownian motion on RD? Well, for starters, we've already said a lot about it when we studied its path properties in lecture 55, for example. All of the results about Hölder continuity of the paths locally and on large timescales applied to Brownian motion in RD. In particular, in lecture 55.2, we showed that on RD, the limb sup as t goes to infinity of the modulus of Brownian motion divided by t to the alpha is infinite for any alpha less than 1/2, almost surely. We can derive some results about hitting times from that directly. For example, for Brownian motion on RD, let's let tr, for a positive number r, denote the hitting time of the exterior of the disk of radius r centered at 0. That is, the disk here I'm using d instead of b so as not to confuse b with Brownian motion. So here we're asking about the infimal time at which the modulus of Brownian motion is bigger than any particular height r. From this result here, even with alpha taken down to 0, we learned that starting at 0, the probability this hitting time is finite is 1 for any r. That is, the Brownian motion almost surely leaves any bounded region. The question is, once it leaves, can it ever return? That's what we'd like to answer in this final lecture of the course. And by the way, this question is equivalent to asking, given the Brownian motion started at 0, does it ever reach a ball of radius r centered at some point x, somewhere far away? Because the Brownian motion with law starting at x is the same as x plus the Brownian motion with law started at 0. So we can always translate, literally, questions about balls centered at x for hitting times to balls centered at 0. The way we will answer this question is by a beautiful connection between Brownian motion and harmonic functions, given by the following theorem that we're going to prove. Let D be any open subset of Euclidean space, and let's denote by tau d the first exit time for the Brownian motion from the region D. Now this is, of course, the debut time of D complement. And since D is open, D complement is closed. And therefore, since it's the debut time of a closed set for a continuous path process, it follows from lecture 56.2 that it is a stopping time. Now, since it's a stopping time, that means that if we evaluate the Brownian motion at that time, that point is in that closed set, D complement. Of course, that's on the event that the time is finite. So this point, the first exit point of Brownian motion from D, is in D complement. But at the same time, BT is in D for all time less than that exit time by definition. And since the path is continuous, as you can see in this picture down here, what that means is that any neighborhood of the point B tau d contains some points that are in D. What that says exactly is that the point B tau d is actually in the boundary of this set D. Now, using that, we can properly state the following theorem. Let f be any bounded measurable function defined on the boundary of D. And measurable here can mean just Lebesgue measurable for this subset of RD. Of course, the boundary of an open set can be very complicated, so there might not be too many measurable functions, but we will usually restrict our attention to the case where both D and its boundary are pretty nice sets. Now define a function u on the open set D as follows. For any point x in D, u at x is the expected value for the process starting in state x of the function f at the exit point for Brownian motion. Of course, that can only be taken on the set where that exit time is finite. So u of x is equal to 0 by definition if the hitting time is infinite. The result is that this function in the open set D is infinitely smooth and is in fact a harmonic function. Its Laplacian is equal to 0 everywhere in the open set. The fact that the Laplacian is coming up here is of course related to the fact that the Laplacian, in the vague sense that we discussed in early lectures on pre-Brownian motion, is the generator of the Feller-Markov process Brownian motion, a topic that we did not have time to get into in more detail in this course, but I hope you will continue in your further studies to understand better. In other words, we can use stochastic processes to find a solution for the Dirichlet problem. The Dirichlet problem is the following PDE. On a region D, we want to find a solution of this partial differential equation, that is, that the Laplacian is equal to 0, which is the statement that u is a harmonic function, with boundary values f. Now I'm being a little fast and loose here because we usually want some kind of continuity. After all, we could just take any harmonic function in the interior and then just define it to be f on the boundary, with no connection between f and what happens in the interior. In fact, with some more work, in the case where the boundary is reasonably nice, you can use this formulation for the function u to show that we will also get continuity of this function u up to and including the boundary, which is the full best kind of solution to the Dirichlet problem. So this is a case where probability theory can be used to provide a solution to a problem in partial differential equations. But we will also see the reverse interplay, where we will use some results from harmonic analysis to then derive consequences about this hitting time and about the Brownian paths themselves. Before we get into that, let's note that what we're really talking about here with this formula is a kind of path integral solution to a partial differential equation. And that is exactly the sort of thing that physicists over the last half century have tried to use in their partial differential equations, like Schrödinger's equation, in quantum mechanics and quantum field theory. And if you like, you can view this as a warm-up for the Feynman-Katz formula, which is a more direct analog to the kind of path integral formulas that you see non-rigorously in quantum field theory literature. We're going to prove this fact now, and to do so, we're going to require the following theorem from harmonic analysis, which gives an alternate characterization of what it means for a function to be harmonic. If D is an open subset of Euclidean space, then a measurable function u on D is harmonic, which means that u is infinitely smooth and has Laplacian 0 on D, if and only if it has the mean value property, which we'll write in the following form. For any point in that open set, and any radius r for which the disk of radius r centered at x is completely contained in D, then the value of that function u at x can be computed as the average value of u on the sphere of radius r around x. That is, we take the function u and we integrate it against the surface measure on the boundary of that d-dimensional disk. This measure here, nu, this is the uniform surface probability measure on the sphere. It sometimes goes under the name of Haar measure, but it's really not that fancy. It's something that you learned how to integrate with in your vector calculus class in spherical polar coordinates. You can do that in d dimensions just as easily with more of those spherical polar coordinates. The key point about this measure is that it is the unique measure on the sphere that is rotationally invariant, which is to say that if I take the set and I rotate it with a rotation in space, that new subset of the sphere will have the same Haar measure as the original unrotated set did before. It's easy to see that there's at most one Borel measure that has that invariance property, and there is, in fact, exactly one, this Haar measure. I'm not going to prove this theorem, but I hope that you will look in appropriate harmonic analysis books for a proof. I should say that this result really goes back to Gauss, so it's nothing new. I also challenge you just from this formula to show at least half of this theorem, that if U has this form, then it is a harmonic function, which is a nice application of the divergence theorem from vector calculus. Moreover, if we're being precise about how this should be stated, being harmonic really could mean that this is true where U is only assumed to have two continuous derivatives. And the result is that if that holds true, then we have this formulation here, and this averaging property implies, in the way that convolution type identities usually do, that the function is actually infinitely smooth. Now, this rotation invariance of the Haar measure plays really well with the rotational invariance of Brownian motion. That is to say, if we take any rotation of Euclidean space, that is a special orthogonal matrix U, and I define the new process Bu of t to be Bt, this d-dimensional Brownian motion, times the matrix U on the left, that new process is still a Brownian motion. And seeing that is again just a matter of checking the covariance. To be clear, you have to check the covariance of each of the components using the theorem that we gave before about one-dimensional Brownian motion determined by its covariance, and then check that the entries remain independent, which is a classical theorem about Gaussians under rotations. Alternatively, we could go back to the result that we proved about the covariance and make a similar statement about d-dimensional Brownian motion being determined by its covariance in terms of the dot product. From this rotation invariance of Brownian motion and the characterization of the Haar measure, it's therefore easy to see that the Brownian motion starting at x exits the disk of radius r centered at x at a point that is Haar distributed, i.e. uniformly distributed, on that sphere. Indeed, as we saw, this point is in the sphere, and if we take any Borel measurable subset of the sphere, then the probability that the Brownian motion at the exit time is in a rotation of that set by a fixed rotation matrix U, well, we can just multiply by U on both sides of here, since U is an isometry. Together, this is the same as the probability that U times B exits the disk in E. But as we saw above, this is the same in distribution as the original Brownian motion. And so that shows us that the law of that original Brownian motion, exit time from the disk, is invariant under rotations, which means that it must be the Haar measure. Now we are set up to prove the connection to the Dirichlet problem. We start with a point x in the open set D, and we define the function u to be the expected value of the function f of the exit point on the event that the exit point exists. We're going to write this in a form that is applicable to the strong Markov property. So we're going to define a function capital F on the path space as follows. F at a path omega is exactly the integrand we see in the definition of U. It's f at omega at the exit time of omega from D, if there is an exit time. Otherwise, it's just defined to be 0. I'm being a little loose with notation here, but of course, this is a well-defined time for any path omega. It's the infimal time at which the path omega is outside D. Now, I claim without proof that this is a cylinder measurable function of the path, and I'll let you think about why that is. Of course, by construction here, that tells us that this u is defined to be the expected value of that function f of our Brownian motion. Now we'd like to use the strong Markov property, which means that we'd like to have, instead of just f of the Brownian motion here, rather f of the Brownian motion shifted by some stopping time. And the way that we're going to apply that in relation to the spherical symmetry that we know that we have is to consider some disk around x that's contained in the region D. That is to say, there will be some ball centered at x, which is completely contained in D. Now, from what we showed about the limb sup of the modulus of Brownian paths in RD, we know that the exit time for the Brownian motion from this ball is almost surely finite. For notational ease, let's denote this exit time from that ball of radius r as sigma. So here on this picture, we have the Brownian motion at time sigma over here. The key observation that I want to make here is that from this setup, since this ball completely surrounds x and is contained in D, any path starting at x that exits D must first pass through the disk here. And that's where we're going to get our shift for the strong Markov property from. That is to say, if I take the function here of a path shifted by this sigma, which is to say the function f on the boundary of D at the path omega composed with the shift at the exit time of D of the path omega composed with the shift on the event that the exit time from D is finite. Well, shifting the path forward in time over to here means that the length of time it takes to get to the exit point over here is shrunk by this amount. But it doesn't change the point of exit. That's what this observation tells us. In order to get over here, I passed through a point over here, and so forgetting this part of the path doesn't change the exit point in so doing. And so in other words, this is just the same as omega at tau d. So this is the same as f at omega. The function we've chosen here is invariant under shifts by times associated to such enclosed disks. So together with this, what that tells us is that u of x, which is the expected value starting in x of f at the Brownian motion, could alternatively be written as the expected value starting in x of f at the Brownian motion composed with the shift by this stopping time, the time of first exit from the disk of radius r centered at x. That sets us up to apply the strong Markov property. Of course, we also need to condition on the appropriate sigma field associated to this stopping time sigma, but we can use the Tower property for that because we're taking an overall expectation here. Now, the strong Markov property tells us that this inside conditional expectation can alternatively be calculated as the expected value starting in some arbitrary point y of f of the unshifted Brownian motion, where y is then evaluated at the random variable b sigma. But taking this function of y is exactly the definition of the function u. That is to say, inside this expectation here, that's exactly u of b sigma. But from what we showed 2 slides ago, sigma being the exit time from a disk centered at x, yields that the rotationally invariant process Brownian motion has b sigma being Haar measure distributed. And so this expectation, by the change of variables formula, is the integral over that sphere of u against that Haar measure. But that is exactly what it means, according to Gauss, for u to be a harmonic function in the region D. And by the way, this function u is equal to f on the boundary, just because if we bend the definition a little bit and allow x to be on the boundary, then the exit time from D is 0, which means that u of x is the expected value of f at b0, conditioned for b0 to bx, which is, of course, f at x. And so that shows us that we do have a solution to the Dirichlet problem here. Now, again, I've been quite loose about continuity considerations at the boundary. As I said, PDE tools can now be used to feed back into probability and show that any such function actually has a unique continuous extension to the boundary if the region D and its boundary are sufficiently regular. The only part of that statement that's going to be needed for us is the easier uniqueness statement, which is to say that if u and v are two functions that are continuous on the closure of D, and both harmonic in the interior, then they must actually be the same function. There's a unique continuous extension of a harmonic function to the boundary, if there is one at all. And that result is an easy application of the maximum principle, which is a core theorem from harmonic analysis that I recommend you read up on. The upshot of all this is that if we can find a function that I'll call u bar, which is continuous on the closure of our open set, and whose restriction to the interior is harmonic, then because its values on the boundary are a measurable function, f being u bar on the boundary, the theorem we just proved is that in that case, the function in the interior is exactly given by this path integral against Brownian motion. And we're going to be able to use that for some particular regions D that are sufficiently nice in order to derive useful information about this exit time for Brownian motion in dimensions 2 and higher. That is, consider the following. For D bigger than or equal to 2, let ud be the following function. In 2 dimensions, it's the log of the length of the vector x. And in dimensions 3 and higher, it's this function here, the length of x to the power 2 minus d. This is a function that decays to 0 as x goes off to infinity. These functions are not defined at x equals 0. They're only defined on Euclidean space with the origin removed. But they're clearly C infinity everywhere except for 0. And from a basic calculus exercise, you can and should check that these are harmonic functions. Their Laplacian is equal to 0 in the appropriate dimension. We're going to use that observation on the region D, little r and big R, which is an open spherical annulus. It's the set of all points in d-dimensional Euclidean space whose length is bigger than r and smaller than capital R. Here's the 2-dimensional version of that region right here. Now let's let TR denote the hitting time of Brownian motion of the disk of radius r, be that the inner one or the outer one or any r in between. Then we can write the exit time of Brownian motion from this annulus, which is of course the infimal time at which the Brownian motion is not in the annulus, as the minimum of t little r and t big R. Our Brownian path where it exits must exit either on the inside circle or the outside circle. And whichever one it gets to first will be this exit time. Now for ease of writing, let's just denote this exit time from the spherical annulus by tau. And so from what we proved throughout this lecture so far, that means that these functions here, which are continuous on this closed spherical annulus, they are smooth everywhere except for 0, which is excluded, that function must be given by this path integral. It's the expected value of Brownian motion started in state x of this function, now thought of just on the boundary, of the Brownian motion at the exit time. That's true for any x in the interior of that annular region. Great. How does that help us? It helps us because we'll be able to tell which one of these is bigger or smaller from that as follows. We know that one of these must be bigger and one must be smaller. And so we can write this expected value as the expected value of this function on the event that the inside sphere is hit first, plus the expected value of this function on the event that the outside sphere is hit first. Now, we know that the point where this hits the sphere is uniformly distributed, but actually with these functions, how it's distributed doesn't matter at all, because this function ud is actually another function, which I'll call ud hat, of just the modulus of x. u2 hat is the log function, and ud hat for d bigger than or equal to 3 is the function r goes to r to the 2 minus d. Now, b tau is a point on the boundary of the annular region, and in the event that t little r is smaller, that means that the exit is in the inner sphere, which is to say that this b tau happens on the inner sphere, which means that this function is just ud hat of little r. Whereas on this event, this is just ud hat of big R. And those aren't random at all. We can pull them out, which means that this is ud hat of little r times the expected value of the indicator of this event, which is the probability of that event, plus ud hat of big R times the probability of this event, which is 1 minus the probability of this event. Now we can solve this equation for the unknown quantity, which is this probability here. And what we find quickly is that that probability is given by this ratio, which I've written out explicitly in the two cases. When d is equal to 2, it's this ratio of differences of logs involving the point x that is in the interior. Whereas in the case d is greater than or equal to 3, it's this ratio of decaying polynomial functions. So that's cool. We've computed another exact formula for this quantity here. How does that help us with anything, though? Well, if you think way back to our discussions of simple random walks, these kind of probabilities, which we used martingale methods to compute explicitly in those cases, allowed us to answer questions about recurrence of the random walk, or transience. And we're going to be able to do the same thing here. So, as a corollary to this, which will be our final result for this course, we have the following. In one dimension, Brownian motion is just plain recurrent. We've already shown that now in the last lecture and earlier. That is, the probability starting in x that 0 is hit, which is the same as the probability starting at 0 that x is hit for any x in the real line, is 1. We also saw that it is null recurrent. The expected value of this almost surely finite time is infinite. Now, we didn't do this back when we were discussing simple random walks, but in fact, that same result holds in 2 dimensions for random walks. 2-dimensional symmetric random walks are also null recurrent. But 3 and higher dimensional random walks are transient. They have a positive probability of never returning to some point. Well, Brownian motion actually doesn't satisfy quite the same hierarchy. In 2 dimensions, Brownian motion is transient. That is, the probability of hitting any fixed point other than your starting point is always 0 in dimension 2. But Brownian motion is neighborhood recurrent, which is the statement that starting at any point x, the probability that you eventually hit the sphere of radius r centered at 0 is 1 for any r greater than 0, regardless of where x is. X could start inside that little ball. It could also start way far away, and we will eventually get to the surface of that ball. But that's only true in 2 dimensions. In 3 dimensions, Brownian motion is neighborhood transient. There is a positive probability that you never reach a particular ball if you didn't start inside it. And the proofs of these follow from the formula that we had on the last slide quite easily, just as in the simple random walk case. First, in the d equals 1 case, we've already done this using different methods from last time. We can compute the exact distribution of this time. But we could also follow the same methods we did here. I didn't write it. In that case, we would need a different function, u1, that is harmonic in 1 dimension. And in that case, you would just use the function u at x equals x. From that, you could derive a very similar formula here. It's just going to be r minus x over r minus little r. And from there, we'll get the same results that we're about to prove. So let's look at the case where d is greater than or equal to 2. The key observation is that tr, the hitting time of the sphere of radius r, that goes to infinity as r goes to infinity. And the reason for that is this complementary result that we proved back in lecture 55. That is, if I take the modulus of Brownian motion and divide by t to the alpha for some alpha bigger than 1/2, then that goes to 0 in lim sup, no matter where we start. So what that means is that the exit time from the sphere of radius r is at least r to the 1 over alpha for all large enough r. If the modulus of bt reached r at an earlier time, then this ratio would not go to 0. But of course, that goes to infinity as r goes to infinity. From that, we have the following simple observation. The probability that the hitting time of the sphere of radius r is finite can then be calculated as the limit as r goes to infinity of the probability that t little r is less than t capital R. And so now we just use the exact formulas that we calculated for these probabilities in the cases d equal to and d bigger than or equal to 3. When d is equal to 2, this is a limit of this ratio of differences of logs. And since log r goes to infinity as r goes to infinity, and these are both staying fixed, that is equal to 1, which is the statement over here. On the other hand, in dimensions 3 and higher, this probability is the limit of this ratio. And now, because when d is greater than or equal to 3, this goes to 0 as capital R goes to infinity, this just tends to the ratio of these two things, which it's more convenient to write with a positive exponent as r over the modulus of x to the power d minus 2. Since x is in the annulus whose inner radius is r, this is strictly less than 1, this is greater than 0, and so that is less than 1, which proves the neighborhood transients of Brownian motion in dimensions 3 and higher. And finally, in the case d equals 2, to see that we actually get transients there, we note that the probability that the hitting time of 0 is less than the hitting time of r is the limit as r goes down to 0 of the probability that t little r is less than t capital R. And now since capital R and x are being held fixed, and minus log r goes to infinity as r goes down to 0, that ratio tends to 0. That was true for any capital R, and so what that tells us is that t0 is bigger than or equal to t capital R almost surely for all positive capital R. But since tr goes to infinity as r goes to infinity, it therefore follows that t0 is infinite almost surely, which shows that in 2 dimensions, Brownian motion is transient. In fact, for any particular point, it almost surely never hits it. That is, of course, not the end of the story for Brownian motion, but is the end of our story in this full year course in probability and stochastic processes.